we'll continue with our probability rules. So we have, we're going to do and or probabilities here, and then this time, many of the probabilities are going to be given to us already, so we're just going to be working with the ones that are given. We have the multiplication rule, and this is going to be for and probabilities. So you have P and B, which is going to be sometimes written as PA intersect B. So the intersection of A and B is going to be the probability of event A happening times the probability of event B happening given event A has already occurred. Okay, so this would be like the probability of getting, if we're doing a coin toss, heads and heads. Okay, but that would be the probability of getting heads a second time times the probability of getting heads given I got heads the first time. Okay, so given something happens the first time. If A and B are known to be independent of each other, then it's just going to be the probability of A times the probability of B. Okay, then we have or probabilities. So when we say can something happen and, so something, the probability of this, and we're going to look at these examples here. Probability of A happening and B happening, that's times. Or, so if you see the word or, that's going to be addition. Okay, so or is P of A or B will be probability of A union B. And then that's going to be the probability of A plus the probability of B. Okay, but if they are not mutually exclusive, then you're going to have to subtract the probability of A and B. If they are known to be mutually exclusive, you can just add them. So probability of A plus the probability of B. Okay, so I know this all sounds very confusing, so let's look at some examples. All right, so this first one, and I might pull some more from your homework because I just have these two right here. All right, so Carlos plays college soccer. Okay, he makes a goal 65% of the time he shoots. Carlos, this is cutting my off again. Carlos is going to attempt 2 goals in a row in the next game. You guys aren't cut off, right? Okay. A is the event Carlos is successful on his first attempt. The probability of A equals 0.65. So that's given to you guys in there. I'm just going to write this down. Okay. B, the event is Carlos is successful on his second attempt, is also 0.65. Okay, because whether he's successful in his second attempt technically should not have anything to do with whether he's successful in his first attempt. There's a probability for each time, so we say this is with replacement. The probability would be the same each time. It's resetting, just like heads and tails. It should not depend on what you do the first time if you get heads and tails. So this is, we would say, with replacement. Okay. Carlos tends to shoot in streaks, however, so the probability that he makes the second goal, given that he made the first goal, then is 90%. So that is the probability that he makes the second goal, given he makes the first goal, would be this. The probability of B given A, because B is the second goal, given he makes the first goal, is 0.90. Okay, so what is the probability that he makes both goals? So that's and. Okay, so both goals, that's going to be and. So we're going to say the probability of A and B, and we're going to go up here. This is going to be our first formula here, okay? So the probability of A and B is going to be the probability of A times the probability of B given A. So let me get a different color here. All right, so the probability of A was 0.65, so 0.65, times the probability of B given A is 0.90. So we're going to multiply those two probabilities together, and then that's going to be the probability that he makes both goals. Okay, so 0.65 times 0.90 is going to give us 0.585. All right, what is the probability that Carlos makes either the first goal or the second goal? So this is now an OR probability. Okay, so this one is going to be, well, we have to look at both of these formulas. So are they mutually exclusive? Can they happen at the same time? You can get the first goal and the second goal? Yeah. You can score first and you could score again, right? Okay. Mutually exclusive is they cannot happen. Like you can't score and not score at the same time. On the same attempt is what we're talking about. So with two different attempts, yes, that's fine. So here we say, no, these are not mutually exclusive. So then we use the first one. Okay, so use this one if they're not mutually exclusive, the first one. If they are mutually exclusive, use the second one. Okay, so here, since they are not mutually exclusive, we are going to do this formula here. So probability of A plus the probability of B minus the probability of A and B. Okay, well the probability of A is 0.65. Probability of B is 0.65, not 0.065. Okay, and the probability of A and B we found right here in part A, which was 0.585. Okay, so we're pulling that down from part A. So we do 0.65 plus 0.65. And then we are going to subtract 0.585. So that'll be 0.715. Okay, then part C, are A and B independent? So independent means we're looking at the probability of A, and then since we're doing the probability of A, probability of B given A. They're going to be independent if those probabilities are equal. Are those probabilities equal? No. Probability of A is 0.65. Probability of B given A is 0.90. That's given in the question. So no, these are not independent. These are dependent. Okay, remember, Carlos shoots in streaks. It says it in the problem. All right, and then part D, are they mutually exclusive? Which we already answered that, right? No, they are not mutually exclusive. okay, because they can happen at the same time. You can score on your first attempt and you can score on your second attempt. Okay, so let's go ahead and look at example 2. Does anybody have any questions? Okay. All right, in a group of 20 college students, 7 are sophomores and 13 are freshmen. Let S be the event that a selected student is a sophomore, and F is the event that a selected student is a freshman. 2 students are randomly selected from this group. Determine the probability of each of the following events. Okay, so this one, we don't really need to use any formulas for this one because they're giving us the actual amounts and not the probabilities. So the formulas at the beginning of the chapter really are going to be necessary when we're doing a problem like example 3.1 because they're giving us the probabilities. They're not giving the number of attempts. Okay? For this one, it is easier to do just by the number in our group. Okay? And let me show you. So we have 20 college students, 7 are sophomore and 13 are freshmen. So we can start with this. You have the probability that a student is a freshman is 13 out of 20. And the probability that a student is a sophomore is 7 out of 20. Okay, so let's think about this. Both selected students are freshmen. So that would be this. You have the probability that you select a freshman times, because both is an and, probability, times the probability that you select a freshman given you already selected a freshman. Okay, which means this. Probability I select a freshman the first time is 13 out of 20. But then this next time when I'm selecting my group, can I select the same person again? In this case. No, I'm not, because I'm talking about people here. So I'm not replacing. So remember, this first one was with replacement, because Carlos reset every time that he scored the goal. This time, I'm selecting students from a group, and I want to select 2. I can't select 2 of the same person. Okay, so this is without replacement. I don't know why I put that S there. Replacement. Okay, which just means this. If I select a freshman the first time, out of 13, I have 12 left that I can pick. And if I selected the first time, any student, I only have 19 left to choose from because I already selected my first student. They're standing off to the side, and then I'm going to go select my next student. So now there's only 19. So that's what changes with the without replacement. My denominator is changing. I'm not putting that person back in my group. Okay, so now we would just multiply these two. So we just multiply straight across. 13 times 12. So 156, 20 times 19, 380. So we'll do 156 divided by 380. And that's going to be 0.411. Yeah, 3 decimal places here. Okay, then the next probability is that the student is a freshman and the second student is a sophomore. So again, I'm not replacing, so when I'm doing my probabilities, I want to do this. The probability that the first student is a freshman times the probability that the second student is a sophomore given, I already picked a freshman. Because remember, I picked that freshman, they're still standing off to the side. So I'm still only going to have, or I'm going to have a different denominator. So the freshman is 13 out of 20. And then sophomore, I have all 7 sophomores still in the group, but I only have 19 left because I picked a freshman the first time. Okay, so then that one I would do 13 times 7. And I'm going to, oops, I think I did put I added a negative sign in. 13 times 7 is 91, and then 19 times 20 is 380. So 91 over 380. We're going to go 0.239. All right, so let's let me give you guys a practice one. I think this one should, yeah, so we'll try this one here. Okay, so take a minute to try this. We just have probability of A is 0.06, probability of B is 0.74, probability of B given A 0.08. Okay, let's take a look. Okay, so we have our given probabilities, and let's see. So first one, determine if A and B are independent or dependent. So remember, for independent, they would need to, the probabilities would need to be equal. So it's the probability, what we're given for the given is with the A here at the end. So you're going to do probability of A, is it equal to the probability of B given A? If I was given A given B, then I would check it with the probability of B. Okay, so always check it with the probability of what's after the given right here. Okay, so the probability of A is 0.06. And the probability of B given A is 0.08. Those are not equal to each other. So we're going to say, no, those are dependent. Yes. So it's the probability of the single event. Is it equal to the probability of the next event given that single event? So I would either check this, or it would be, is this equal A given B? Okay, so the after the given is always going to be equal to that single event, what you're looking at there. But we weren't given A given B, so I'm not going to look at that. I'm using what we were given because I actually don't even know what these probabilities are for. I'm just given the numbers. Okay, now the probability of A and B, since we know that they're dependent, that is the formula where we are doing the probability of A times the probability of B given A. Okay, that's your AND formula, the very first one we gave in this section. So the probability of A is 0.06. Probability of B given A is 0.08. So I am multiplying these. So 0.06 times 0.08, 0.0048, and 3 decimal places, so 0.005. Okay, now determine if A and B are mutually exclusive or mutually non-exclusive. And I think that I gave this to you guys in the notes in the last class. We aren't given any context of the situation, so we assume that they are mutually not mutually exclusive. I want to make sure that that's in the notes, because if it's not, I'm going to add it in. Yes. Important note, always assume 2 or more events are mutually non-exclusive unless you can show otherwise. So we actually don't know what these probabilities are for. We're not given any information about it, so we're just going to assume they're not mutually exclusive. Okay, so this is, what does it say? It says mutually non-exclusive. And then the probability of A or B. So the probability of A or B when we are not mutually exclusive is the probability of A plus the probability of B minus the probability of A and B. Okay, so we minus out that probability of the and events when they're not mutually exclusive. When they are, we just add them singularly. All the formulas, again, you guys had the formula sheet from the first test. These are all there under Chapter 3. Okay, so the probability of A is 0.06. We're going to add probability of B, 0.74, which I think is just 0.80. And then we're going to subtract not B given A, P, A, and B, which is what we found up here, so 0.005. Okay, so that is going to be 0.06 plus 0.74 is 0.8 minus 0.005. Gives us 0.795. There we go. So that is question 9 on your homework. Okay. So going back to the notes, we're going to go to section 3.4, and we have contingency tables. I get some different colors in here. All right, we'll use that one. Okay. Contingency tables, I like these. They're easy to read. Easy to pick out the information from. All right, once you get the hang of them after a couple times, pretty easy. These are called two-way tables. All right, marginal probability is I have all these things happening at the same time. So if I look down, just kind of take a glance down at the table, you have male, female, left-handed, right-handed. So we have two things that could happen on either side. You could be male or female, or you could be, you could be right-handed, or you could be left-handed. So two different things happening, so we have two-way tables to sort these out. So marginal probability is going to be the probability of a single event without consideration of another event. Okay, so it's just a single probability, and this is really just more of a vocab question for you guys. All right, so let's look at this two-way table, and we're just going to do all of these probabilities. So we have the contingency table below describes a distribution of a random sample of 100 individuals. This is 100. That's the total, complete total, organized by sex and whether they are left or right-handed. So when I get a two-way table, what I first want to do is I want to add total columns in on either side, just so I know what my totals are when I'm doing my probabilities. So if I add across on the males, I have 43 plus 9, so that would give me 52. So I have a total of 52 males. And then if I add females, 44 plus 4, that's going to be 48. And then I can add the right-handed. So right-handed, you have 43 plus 44. That's going to be 87. And left-handed, 9 plus 4 is going to be 13. And then if I add these, 87 plus 13 is 100, and 52 plus 48 is 100. So they should add to be the same, both down and across. Okay, so first thing is the probability of males. So this is, okay, probability of male just in my total group. I'm going to take all of these, so everyone has their own slip of paper. Male, we'll assign them all numbers, okay? And it'll be male, left hand, what they have on each. Okay, so the probability that I pull it out and it's male, without consideration of whether it's left or right, 52 men out of 100 slips of paper. So 0.52. Female, 48 out of 100, 0.48. Right-handed, I have a total of how many right hands? 87 out of 100. So 0.87. And left-handed? 13 out of 100. 0.13. Okay, now here's why I like two-way tables, because when I start getting to the and the or, the given probabilities, I don't have to use these first four probabilities computed. I can actually do it just from the table, looking at the table, okay, because I'm going to be able to sort out my different denominators. So when I'm looking at this, I have probability of M and R. So for that, if I get my highlighter here, males that are right-handed are right here. So I'm just looking at that 43. So there's 43 right-handed males out of a total. Again, this is out of 100. So I gotta get my pen back. So this would be male and right-handed, 43 out of 100. So 0.43. Okay, probability female and left-handed. So here I go to female, and I go left-handed, and that gives me 4. So I'm looking at this one right here. So that's 4 out of 100. So that would be 0.04. Okay, probability male or female. How many males do I have? And females? How many total is that? 100. Is that okay? Yeah, what's that probability? 1. Probability has to be between 0 and 1. Can't be above 1. Okay? But any one I pull out of that hat is going to be male or female. Okay, probability female or left-handed. Okay, so here I have, you can be female, which would take the total number of females, 48, plus any left-handeds. So I already accounted for these, so I'm looking at this one, and this one for female or left-handed. So it can be any of those three. So if I added those together, so 48 plus 9, or we could do 44 plus 4 plus 9, that would give me 57. So that's 0.57. Erase that. Okay, next one is not probability of male, it's probability not male. It's with the line over it, or it's M apostrophe. Remember that from the first section? That's the complement. So that's just 1 minus the probability of male, which in this case, since it's a two-way table, it would just be whatever the probability of female is, but it's just 1 minus 0.52, which is 0.48, which happens to be the same as female. Okay, then the givens. So this is right-handed given male. Should just be a little bit longer here. Okay, remember when I said when we were learning the given probability, that's the denominator. So if it's right-handed given male, I'm going to first only look at the total number of males, 52. Okay, so given that it's a male, what's the probability that person's right-handed? Well, there's 40, and I'm only looking at right-handed males. So I'm only looking at this first column, so there's 43 right-handed males out of a total of 52 males. So that's right-handed given male. So then that would be 43 divided by 52. 0.827. Okay, then you have probability of female given left-handed. Okay, so now my denominator is the total number of left-handeds. So now I'm looking at the second column down. So total number of left-hand is 13. In that column, I have 4 females. So 4 out of 13. So 4 divided by 13, 0.308. And then probability left-handed given female, that would be denominator of female, 48. And then out of the females, only 4 were left-handed. So 4 out of 48. So 0.083. Okay, so when you're given the two-way tables, you're just picking out the probabilities. You don't have to use the formulas. If you're given just the probability, like we did in the last couple of examples, then you have to use the formulas. So why don't you guys try example 4.2 with the hikers? And there are some missing values, but you guys can figure those out because that's just simple addition. All right, let's go ahead and take a look at example 4.2. So we have the contingency table shows a random sample of 100 hikers and their favorite hiking location. So we're missing some values. So let's see. Female, what's missing here for mountains? 11. So how we get that, if the total's 45, then we would do 45 minus 18 minus 16. That would give you 11. Okay, then let's see. Well, we could do 11 plus 14 down here would be 25 for the total. And let's see, 45 plus 55 should be 100, which means we can fill this in because it would be 100 minus 25 minus 41 would give us what? 34. Which means then I can fill this part in, 16, 34 minus 18, and then also here 41 minus 16, 25. So those are your missing values. All right, so first one, probability of, oh, we're missing all of this here. So you have M is male, F is female, we have, let's see here, F give, or wait, what does it say here? C is coasts, D desert, and then MTN for mountain. All right, so first P of M, so probability of a male. Total number of men, 55 out of 100, so 0.55. For C, probability of female, how many females? 45 out of 100, 0.45. All right, C, probability of female given the favorite location is the coast. So what's the denominator there? 34, good. So 34 total, like the coasts, and then out of that 34, how many are female? 18. So then 18 divided by 34 is going to be what? 0.529. All right, D, you have probability of men given desert. So how many men, how many total desert? 41, so that's the denominator. And then out of the desert, number of men? 25. So 25 divided by 41, 0.610. Okay, so for E, the and, we hadn't done an and probability with the tables, so it's female and desert. So this is, for the and probability, the denominator doesn't change. So the denominator there is 100. And what you're looking at is out of the total 100, if I had all of these in a hat, what's the probability that they would have both female and desert as their designation? So there you're just looking right there at that. So 16 out of everything on here, out of a total of 100, had female and desert on it at the same time. So 16 out of 100, 0.16. And then we'll come back down to the other stuff. Okay, so then you have probability of, coast and male. So again, that's out of a total of 100 for the and then coast and male, we would go male, coast, where they meet, 16. So 16 again. Okay, then or, female or mountain. So I'm going to go ahead and pull a name out of the hat, and it could either be female or mountain. So it's out of 100. So here I would do total number of females. So 18, 16, and 11, so 45. Plus any men that also like mountains, because those could be included there as well. Because they just have to have female or mountain as one of the designators. So it would be 45 plus 14. So 59 out of 100, 0.59. Okay, so when I'm looking at that, that's any female or mountain. So it would be these three plus the 14 men that like mountains as well. So then same thing here, coast or desert. So anyone who likes the coast or the desert. So that could be any of these or these. So really 34 plus 41. Which is 75 out of 100. So 0.75. And then this again is supposed to be a complement with a line over it. It just didn't print. So the probability not female, 0.55. That's just probability of male. And then same thing for K. So probability of not coast would be 1 minus the probability of coasts, which we did not find actually. So the probability of coasts is 0.34. Total number of coasts. So 1 minus 0.34, 0.66. All right, are the events M and D independent? So you could either do the probability of M, is that equal to the probability of M given, D given M? Or you could do the probability of D, is that equal to the probability of M given D? Either one of those. So let's see what we have. We have M given D. So the probability of M given D is 0.610. Probability of D, total number of deserts is 41, so that's 0.41. So those are not equal to each other. So we say, nope, these are not independent. And as you guys are starting to see with all of these examples, we haven't had an example where they are independent yet. Okay, so most of the time, it's going to be dependent. What about mutually exclusive? Can you like the desert and like the coast at the same time? Well, you could, technically, but in this case, you had to pick one, right? You had to pick one. So, no, they cannot happen at the same time, which means, yes, they are mutually exclusive. M and D are not independent. Not independent. So for them to be independent, the probabilities would have to equal each other for the givens.